Yeah, so welcome to this webinar. Good morning or good evening, depending on the part of the world where you are today. My name is Carlos Rivera. Have the pleasure today to give you an overview about the new release FEFLOW A1. That's a release webinar. So the webinar is divided in two parts. So we will have a first overview through the PowerPoint about the new features. And in the second part of the webinar, I will do a live demonstration. Okay, so in this webinar, we have a different groups of features that we have implemented in the version 8.1. So we have a new integration with CAT. So we support new CAT formats and number of additional things. We have been working quite a lot in the well manager, implemented rules to manipulate wells and others. For those working in the geothermal sector, we have a lot of developments for geothermal applications, open loop and closed loop systems. We have a new way to control data from the FEFLOW interface with a new panel called or new dialog called observation data dialog, which control all the information. We have a lot of changes in Python and more developments on the 3D super mesh. Yes, I see Nico is raising your hand. So if you have any question, Nico, please use the chat or the Q&A panel in Zoom. I'm going to take care of the different questions at the end of the webinar. I think okay, maybe Evan, Nico is having some problems with the audio. Could you try to help him or write him on the chat? Thank you. Okay. So to start, so we have this new CAT integration. The new CAT integration, basically, we have re-implemented the way how FEFLOW is working with CATs. This implementation, which exists already since a number of years, in many years actually, has been totally renewed in this release. So we use the state-of-the-art package called Open Design Alliance. So DHI is member of this alliance. And this is a SDK package which allow us to manipulate easily new file formats, DXed file formats. So we are supporting the latest file formats from AutoCAD. We introduce a new support of DWG formats. And also in this release, we have a first introduction of support of 3D solids in FEFLOW. I say it's the first introduction or the first implementation of 3D solids because in the CAD world, a definition of a solid could vary quite a lot. So we decided to implement some of them, but in the next releases, we are going to have to add additional ones depending on your requirements. So this is example of a 3D super mesh or being used or being built from AutoCAD DWG file. As any other file format in FEFLOW, you can just simply do right-click on the maps panel, import the map, and then FEFLOW will take care of this. Well Manager, we have a lot of major improvements on the Well Manager. The Well Manager is a very popular tool which was introduced initially with the FEFLOW version A0. The Well Manager has the function or the ability to create any type of well BC, multi-layer well, borehole heat exchanger from the same location. You can easily create wells from selections or just simply type in the wells, the coordinates of the wells and the rest of the parameters directly from this tabular view. You can import, export information, and you can always also nicely combine transport boundary conditions, which is something unique in FEFLOW because in one location you can apply flow, mass, and heat transport boundaries. So we decided to extend these applications in this release. And for that, we have a major extension which allow you to create groups of wells. Why do you need to create groups of wells? Because these groups will have some operational rules. We call it rules because will allow us in the future to extend all these different applications. For the moment, we have, for the flow part, we have 3 rules. You can have of wells being grouped, and the group can be active or inactive. So this is something really nice in case you would like to do some tests. What's going to happen if I completely turn off a number of wells? You can share the properties within a group, meaning if the number of wells are inside a group, and this group has the rule share properties, the members of the group will inheritance the properties of the parents of the group name. Distributed flow rate. This can be used in cases where you know approximately what is the total flow rate of 100 or 200 wells, and you would like to equally distribute it in space and in time. So FEFLOW will automatically distribute this, and you can also combine any of these three different rules with well VCs or multi-layer wells. For the case of geothermal applications, we use the same approach of rules, and we created two additional rules, which are only available in the case where you have the heat problem class activated. And what we are doing this, so you probably have been noticed that DHI in the last months introduced a new geothermal subscription. So we are doing a lot of improvements on the geothermal sector application. So one of these highlights of the subscription is it has the capabilities to operate with the FEFLOW advanced module of features, which was not available before for the heat problem class. The reason of that is because we have seen a lot of demands on complex geometries being used in the geothermal sector, like inclined boreholes or deviated boreholes, or even for deep geothermal applications where FEFLOW is used, complex geometries are occurring, so you will need to build 3D and structure meshes for that. So coming back to the well manager, so what we have done is we introduced two operational rules, which are called open loop system and closed loop system. In the case of the open loop system, this rule will entirely replace the old plugin called open loop plugin. This plugin, if you have been working in the geothermal market with FEFLOW, this plugin is already existing more than 15, 20 years. It's an old implementation which was not up to date. So we have reinvented this and implemented directly into FEFLOW. So you don't need to use anymore the plugin. From our different tests, we realized that there is a significant improvement in the performance between the plugin and the new implementation directly in FEFLOW A1. And how it works, you group the wells, tuplets or triplets, if depending when you want to model, and then you apply the open loop rule. You define the temperature difference between the injection and production wells, and FEFLOW graphical interface will take care of the rest. For the case of closed loop system, this was needs due to the high demands of FEFLOW users, especially in Europe, working with borehole heat exchangers. There was the typical limitation of working with hundreds or even more of borehole heat exchangers, which has to be interconnected. The interface or FEFLOW allow you to create borehole heat exchangers since probably before version 6.2, so even in the version 5 was possible to implement that. But there was no significant tools to connect them. So you could connect a number of boreholes easily if you talk about 5 to 10, but if you see now the geothermal projects that are happening right now, they are working with a lot of a high number of boreholes, which makes a little bit complicated to work with FEFLOW. So we introduced this new operation rule called closed loop system, which allow you to group the boreholes. In the example, I have 33, but could be more. You can define a pattern of the operation, which will be parallel, serial, or custom. Custom means that it's anything else beside parallel or serial. You provide a flow rate, the type of input for the energy, for the heat boundary condition, either a power, inlet temperature, heat input rate, or energy, and the value depending on the type of energy or type of information. Power will be in joules per day. If will be energy, will be in kilowatts or megawatts hour, for example. And that tool, nicely, what it does, connects all the different boreholes and automatically. So what before it took you a lot of time to connect all these different boreholes, so you can just simply do it with maximum 3 clicks. Observation data. You see, we have a number of ways how we can evaluate the different model results. So model results could be process variables like hydraulic head, concentration, temperature, or age, species, etc. But you also look for budget groups, so you want to see how much comes into a river or leave from the river into the aquifer. Or if you are doing content analysis, you would like to know how much volume or how much energy is stored in one elemental selection. So you have a lot of options or a lot of results. What we have doing with this change is we try to bring everything closer together. So one location where you can control everything. Why? Because from this interface, what is called now, or dialog, what is called observation data, you can easily review all the settings that you require. So the number of observation points, the budget groups, the content domains. You could define a number of settings for verifying these different options, starting with the observation points. So what is new with the observation points is you can group the observation points. So I create my group Atlas Hof or KB, and these groups will allow you to control, activate or deactivate the observation points within the group. If you use the groups and then you connect later this FEFLOW file with FEPES, FEPES will recognize that you have groups, and it will create so-called observation definitions depending on the different groups that you have, which is really, really nice, because in the past you have a number of observations. If you import the observations into FEPES, FEPES is going to create one single observation definition with all the different lists of observation points from FEFLOW. And normally you would like to just wait for the PES calibration or other different settings. Now with the groups, we can do it directly. There is a smart synchronization of the core attributes. So if you would like to compare some measurement data with simulated values, you need to first add the information that you would like to compare. That's a bit different how it was done in the past. In the past, you see all the different lists of columns and parameters. So we try to reduce this by only offer you, or you decide actually the information that you would like to see. So you can attach here a time series or a constant value if you want to compare the hydraulic heads between model results and observed values. In the case of observations, it's also very nice, even if you don't want to compare your observation values or your simulated values of budget groups with measuring data. So if you have a river and you say you store the selection of the nodes along the river and then activate budget history charting boundary conditions, you can compare this if you want. But the other possibility is from the interface with just simply clicking, you can choose a number of selections. So the interface will give you the list of selections. You can group them and tell them all these selections will require a recording of the boundary conditions budgets. Maybe the other group, I would like to have the storage capture release, and maybe I have special locations or where I would like to separately monitor the imbalance for the flow rate, or the mass rate, or the heat rate. Again, on demand, you can attach a number of columns to compare data for the period or for the rate budgets. Analog is for the case of content domains. Content domains is not something much used in FEFLOW, so we have something called content panel, which work or operate with elemental selections. On these selections, you can activate some fluid, mass, or heat options. So for the fluid, for example, you could record it in the selection, or you can investigate what is the amount of volume inside this subdomain of the system. This could create a chart, and the chart will be visible during the run and also stored in the DAG file. You can activate all these different processes directly from this interface. And if you have the data, you can also compare the simulated values with the observed values directly from here. Okay, FEFLOW and Python. So this is something really, really nice, and something where I like a lot the way how we move in this direction, because we have been doing a lot of IFM programming since more than 20 years. So FEFLOW has an open programming interface initially in C++, which is probably 25 years old. And also we have extension of Python, which is probably now more than 10 years. Yes, because we introduced it in 6.2, 10 years exactly. So we have a lot of methods which are available in Python. We know that the users like to operate with Python. So there are a lot of things that you can do now with the IFN interface in Python or in C++. So if you have a FEFLOW model, this was always a requirement. You have a FEFLOW model, and with this FEFLOW model, you can set material properties, activate, deactivate boundary conditions, change values, run the simulation, store the results. So it's a lot of things that you can do, but it was missing the part of the super mesh. And this is what we have introduced now in this release. So we have a Python interface for super meshes. This is a module called PySMH, so Python Super Mesh, is the abbreviation, and is offered as a SMA benefit. Means if you have a valid FEFLOW A1 license and you are granted to the FEFLOW Advanced module because of the SMA, you will get the new version 2.0, which includes GOD package for the 3D super mesh repair and remesh, but also this package for Python interactions with the super mesh. So what is it in this package? So you have the possibility to create and edit existing super mesh. If you create a super mesh, you can add a number of super mesh elements. Super mesh elements will be points, polygons, and lines. Super mesh properties, you can define the number of slices, elevation data, material properties. From Python, we run the mesh generators, triangle, grid builder, etc. And from Python, we can extend the 2D mesh to a 3D mesh. So technically speaking, with this new implementation of IFM for super meshes, you have one single workflow from the beginning, from starting the super mesh until the end, because the parameterization part, running the calculations, saving the results, it was already implemented since many years ago. Saying we have another extension in Python for cross-sections. So this was always the wish. So how do we create easily cross-sections in FEFLOW? In FEFLOW, you have a cross-section mechanism which depends on the 2D line. So we use a similar approach in Python. So you can have a FEFLOW document, which is a 3D document, draw a line, you know the coordinates of your cross-section, so you can import this line if you have it as a shed file, and then in Python extract the coordinates of the line. And then we have a new method called create mesh from plane. And this method, what it's doing, it's basically replicating what FEFLOW does in the graphical interface. It will cut the model through this line, create a cross-section, and it will extract a pseudo mesh. We call a pseudo mesh because it's a mesh which has been cut by the planes. So this is what you will see in the FEFLOW graphical interface when you open a cross-section. This mesh is accessible in Python. So you can get it through these methods. Since it's a mesh, since it has a number of nodes, elements, you can apply it any of the existing methods for in the open programming interface. For example, you can get mesh get values to extract in one single shot all the values of hydraulic heads. You can get number of nodes, or you can get number of elements and then plot it. So here is a little example using PyVistas to plot in some, not heads, but plotting some colors, which comes from the elemental distribution. So we have some geological ID, which have been stored in different element blocks, and I'm just basically using the method and then later plotting this in Python. So this is a nice implementation for FEFLOW and Python interfaces. 3D super mesh. So we introduced in the version 8.0 the few improvements about 3D and structure meshes. So we have the possibility to repair or remesh surfaces, which increase the probabilities to create a full structure mesh. I say increase the probabilities because we are aware there are some cases where we need certain improvements. So we are working on that, and we will be working in this topic intensively in the next months. As a news, we sign a collaboration with GOD in France for the next 5 years, where we will improve a lot of unstructured meshes on different workflows. So to help you with these workflows in the FEFLOW A1, we have worked a lot in the 3D super mesh. We start from a 3D super mesh where there was actually nothing in case if you want to digitalize any geometry, you are always depending on external files. So you import your geological model or you import your shed files, and FEFLOW use these maps data to convert to super meshes, and depending on that, you build your whole domain and then the 3D and structure mesh. So we have now a number of tools, and these tools are allowing you to create polygons, super mesh polygons. So you can just digitalize the polygons in 3D and then build your surfaces. You can create planes. So if you have a fold with certain inclination, you can draw this fold. This already exists in the previous version. So what we have now is we implement the possibility to create a so-called fold zone where you can define parallel planes in case you would like to maintain small discretization around the fold planes. We have a tool called bonding, super mesh bonding surface, which one surface you can just import your digital elevation model, which is vector file, let's say, in a shed file, or could be any other format, a DXZ file. And then you can tell in FEFLOW, I would like to extend and extrude the model and create a 3D domain with just one surface. We have tools for selection. You can select different parts of the super mesh and also to delete them. This is quite needed because in the past, there was only the problems of the intersection were happening in one location, and you wanted to just modify that part and it was not possible. Now you can just select and delete or edit. We have some snapping functionalities in 3D. So if you would like to digitalize, we have the possibility to plot a map and then digitalize based on snapping distance. And we have the possibility to include satellite points in 2D and 3D. This is the case on 2D, especially for those working in the geothermal sector. If you remember, we use a lot this rule of ideal element size, where the size of the discretization around the borehole depends on the radius of the borehole, which you will typically manage by creating auxiliary points. So now we have a nice tool which allow you to automatically create these points in 2D and 3D. You can also export the 3D super meshes. So this was one of the requirements from one user in Canada, so which was trying a lot the repair, and in some cases the mesh was quite good, and he wanted to have that mesh and use it for other purposes. So we just try to develop this. And there are also another number of improvements in terms of the super mesh. So to give you an example of the potential workflow that you have today, so it's a simple workflow, which I will try to use in the demonstration. So you have a surface, the surface with a new tool, you can extrude the surface and build the domain. You can use the plane tool with the buffer to create some folds with certain inclination. You can repair these tools. In the case the planes here are above the topography or below the base of the model. And finally, you color remesh to retriangulate the surfaces of the super mesh. And the last point is to construct a fully structured mesh with GeoD or with TechGen. And with this, I would like to move to the live demonstration. In the live demonstration, I have few things. So I will start with the Python actually interface. So you see my screen, let me create another file here. It's called demo. And since I've been, to save some time, I will not type all the different parts of the script, but what I will do is basically show you a few things on the screen so that you understand what is the logic behind. So what we would like to do is basically to create a super mesh. So the first part you can ignore is just to define some files. So the method will allow you to create documents. We are creating an empty document, and from this document we are extracting the super mesh. So if I print this saying the super mesh, by the way, we have a lot of improvements in the print method. So you can print lookup tables, variables, or classes of super mesh, and then FEFLOW will give you the information. So in this case, it's not going to tell me much because there is nothing. This extension of the super mesh is 0, 0. It didn't define anything. So let's start building a simple box. And this simple box works like this. You require an origin, and then you require also at least one element, which is a polygon. So I'm defining a box of 7 by 7 kilometers. So this is gonna be later a deep geothermal model, a 7 kilometer box, and we will add some boreholes. So I would like to, for example, save the super mesh now. Would like this, and if I save it, it's gonna create a super mesh file in my super mesh folder, and I'm gonna open it now. And the super mesh is gonna be a simple box of 7 kilometers by 7 kilometers. Okay, that's nothing impressive, so we can do a lot of additional things. So what I would like to do is I would like to put 2 boreholes, because we said we want to have a geothermal system. I have 2 points. One will be the injection well and the other will be the production well. And to control the discretization, I will put a number of auxiliary points around. I have calculated the coordinates in Excel, so I know the points around. So if we run this again, then we can immediately reload the file, and then we will see that we have the additional points in the super mesh. It looked like 2 points, but if we zoom around, it was too much. So we will see that we have the injection well or the production well and around six auxiliary nodes to control the discretization. Okay, so still is very, very simple. So what can we do else? So we can start adding additional information. So let's create a mesh. So we like to create a mesh. So let me put this one here. We need to start defining the mesh generator. And so you have a method which will allow you to get the mesh generator, and the mesh generator in this case is triangle. And basically here you have a full access to all the different settings of the mesh generator. And use only 3 of them: refine points, gradation, and the point target size for the mesh generator. So these are the mesh generator properties, and I'm also setting properties to the whole project. I have maximum 5,000 proposed elements. So if we run this, so I would like not to save the super mesh, I would like to save the FEM document, so we can run it. It should take just another second, and if we open this, we can see that the super mesh or the find element problem is created. So we have now the mesh in 2D. If I look the meshing panel and I look from super mesh elements, I have the value of 5,000. And I have the discretization around the points because I told that I would like to have this. So I can easily change the mesh, change the number of elements or other settings directly here. Okay, next step, we would like to create a 3D mesh. So to create a 3D mesh, before we call the mesh generator, we need to set some properties, and the properties are the slices. When we introduce in 7.5 the possibility to have slices in the 2D super mesh, it was already with the vision to extend the IFM interface in that manner. So what I'm doing is now I'm defining first an interpolation method. So I would like to use FEFLOW, invert this as interpolation method in Python, and I would like to set some properties of always using 10 neighbors for interpolation. I have a file which it's called topography dot, and just have 3 columns, X, Y, Z. It could be a dot file, it could be a shed file, basically the different point data supported by FEFLOW. And then I just add a number of slices. I can define the elevation. The first slice will be interpolated, then the second and consecutive slices that are depending on the previous one. So I'm saying one slice will be 50 meters below the previous one, 100, 150, and so on. And the last slice, which defines the base of the model, it has elevation of minus 1,000 meters. So as I was saying, that the domain is quite large. So we initially is a model which is intended for deep geothermal applications. So we can look here, and if I manage to make larger this panel, So what is happening is something very interesting, what is actually done on purpose to demonstrate. So I'm interpolating and the topography, and then I'm moving the slices in some fixed layer thickness. In some locations, there is an intersection because of the thickness, and the method already has a correction approach, which will keep a minimum slice distance. At the moment, it's not possible to change the slice distance, but this is something that we should definitely introduce in the next releases. So I have run the script, finished with 0, and if we open the reload the file, actually reload, I hope I save it in the script. Yes, after I set the elevation, there was the same block of generation. Now we can see that the model we have created a 3D mesh directly from Python. And to conclude this exercise, what I will do is to show you also a new approach, what we call problem definition. So here, if you're satisfied with the mesh, with the layer mesh, with the triangulation in the slice view, but also with the vertical discretization, the next step is obviously to define the problem class. And this is also done directly from Python. So if we go here to the problem settings, we will see that we are working with a standard and transient fluid flow. But let's add some heat to the problem. And for this, we need a new method called getProblemDefinition, which is a class in Python. And this class gives you access to a function called setProblemClass, which could define the FEFLOW problem class, flow, mass, or heat, or all together that are called in FEFLOW thermo-aligned problems. You can say whether the system is steady or is transient, whether the system is saturated or unsaturated. Unsaturated means Richard's equation. If it's saturated and you would like to solve as a confined, there is another function to define the different settings what you will have in the phreatic mode. So if you want to have, for example, the first slice being free or movable or phreatic, and the next one's depending on the last one being fixed, you can also define it through Python. So if we run the script, it will take another second, so it's done, or almost done. Yep. If we reload the file, we can see that now FEFLOW has set the problem class to heat and steady state. Heat and steady state. So literally with this, for those ones who are working with models which are simple box models like this one for geothermal applications, literally you can build your models in basically almost no time. For complex models, it's obviously applicable, so you will need to define the elevations in the different slices, and the interpolator will do the job. What it's basically really doing is just following the same concepts that we have in the layer configurator. So we are calling the layer configurator from Python, and what you have seen, the extraction of the 3D model is exactly the same extraction that we will have here in this extension to 3D. It's exactly the same. Okay, so that was the demonstration with PySMH. So let me change the topic to some well manager examples. So let's see if I can manage. So this is a model where we have already discretized it. It's a 3D model. We have a number of slices. And if I go to the slice number 3 and activate, we have a number of different selections of edges which will define boreholes, multi-layer wells. So we can go to edit, well manager, and there are no boreholes. So I can simply activate this, the selection. I see the selection on the background, and if I go to the list of options and say add multi-layer well from selections and one click, I will introduce immediately the 20 boreholes or multi-layer wells. Requirement is you need to create the boreholes first, and you create them when you apply it. So when you apply, you already see that you have the multi-layer wells in the well manager. New is now the possibility to group and group and group properties. So if we go here to this auction, so we see we have 20 wells and all of them are active. If you would like to group, you just basically need to select them and then click on group and create. So let's call this groundwater management. It creates a group so that the group name appears next to the borehole. We apply it, and now we go to the group properties. So we have the groups. If you have different types of boundary conditions or multi-layer wells, well disease or borehole heat exchangers, you will see different lists. Here we have multi-layer wells, one group, which contains 20 wells, and here we have the group. So what I will do is I would like to basically easily say that all of them will like to have a pump rate of 10 cubic, that was too fast, of 10 cubic meters per day. So 10 cubic meters per day, the radius I'm using the default. If I click on applied, okay, I will see immediately the tanks appears in the list. It's updated. There is a lock, which means you cannot really edit it from here because they are grouped. If you would like to edit few of these boreholes individually, what you need to do is basically click on the ones that you would like to edit manually and ungroup them. So now if we go apply, okay, and let me save the file. Let's put here a X. And if we now clear the selection and we go to the rate budget panel, activate, and now we start the simulation, we should see we have 20 multi-layer wells, 10 cubic meters per day, 200 is what we expected. And if we zoom closely and deactivate, so we should also see in the deeper slices that there is some drawdown. We need to activate this so you can slightly see this, the drawdown, because of the low pumping rate that I'm setting. Okay, so what can you do with this? So let's say we would like to do a test, and I would like to take these 5 out of the group and just deactivate them. So I can ungroup. Sorry, that was not good. So I can activate the 5 boreholes. Doesn't matter the name. The number 3, let's say, ungroup them so they are independent. They can be edited now, and you can put any number. 3. I can make them be depending in another group. So this will be the inactive wells, and apply. If we go to the group properties, we have now second group, which consists in 3 wells, and this will become inactive. Apply. So you can combine also different properties. So if I apply the rule, so I can say this will be hundreds. But since it's inactive, it's not gonna do anything with this. So if you can see the wells are gray out, they will not participate in the calculation. So if we run the problem, then we should see some decrease in the pumping rate. So we in the total domain, the rate budget. Okay, so that is what I would like to show you with well manager. Another possibility, just one thing, I would like to group them back to this, and automatically we'll get the properties of the group. We have 20 with this value. We have 20 times 10 is 200. We can do a dummy exercise where I distribute exactly the same. I can add a distributed flow rate rule, which basically will bring the same results of the previous exercises because it's just splitting equally. To make it maybe more interesting, what you can also apply in these cases, if we have this one here. It's the same file, but it's this time is a transient. We have a time series, what we call well sets, and this time series can be also applied as a part of the distributed flow rate. So if you are changing the flow rate for the whole group, FEFLOW automatically will split it equally in all the members of the group. Yeah. Okay, so now that you know the basic operation of the well manager, so let's try to do some hit operations. For that, we need a different file. And we can get it from here. Okay, so in this file, we have already discretized some locations for the borehole heat exchangers and 2 locations for a for an open loop system. So let me reset the initial temperature of the system to 10 degrees. 10 degrees. To save some time, I have already prepared the boreholes, so I can just simply import this list of boreholes from my example data sets, which I need to get it now here. And what it has is injection extraction. This is part of the open loop. I have already connected the time series. We have 3 borehole heat exchangers. So we're gonna create an open loop system. So we need to first group them. So this will be the open loop. And the 3 will be the so-called closed loop. Okay, apply. Then they are just grouped. Nothing is being set inside the group. We can go to the properties for the open loop system. What will replace immediately the all plugin is this possibility to create operational rule called open loop, where you can define the temperature difference. So we have a time series where it keeps the delta T in between the inlet and production boreholes. You can also control the flow rates and all the information with the other rules if you want. So I have, yes, apply, need to apply first. And it happened that I have another group empty. So here now we have the closed loop rule where I will have 3 boreholes. I would like to have a parallel distribution. I would like to have a constant flow rates. The input time will be power, and we'd like to have 3 kilowatts. Applied, and then okay. And what is happening? The properties are updated for the case of the closed loop. There is a lock because you cannot change part of the group. And if we now save it and we start the simulation, we should see in the average temperature a number of different curves for either the multi-layer wells, but also the borehole heat exchanger. So if I deactivate the mesh, I can see this is the location of the injection well. So where we are using always a temperature of 3 degrees, delta 3 degrees minus 3. So we start with 10, we re-injected 7 degrees. If we look now the time series of the average temperature, we will see that we have 2 lines. So the one with is 10. At the moment, the production well is still with 10 degrees, this location. The injection will be 10 minus 3, 7. And we have a number of curves corresponding to the 3 different borehole heat exchangers. These 3, they are exactly the same because we are using a parallel distribution or parallel pattern for the closed loop rule. Okay, so I see I'm running out of time, but I would like to do the last example. And for that, we change the topic completely to the case of, or to the demonstration of 3D unstructured meshes. So let me open first a simple file that I have to save some time. So that's a surface. This could be a shed file, could be a DXF or DW file, so anything that is supported by FEFLOW. The only rule is that it needs to contain 3D information so that we can plot it. So you can see from the mesh menu, we have a number of new tools to add points, polylines, polygons, planes, and so on. To interactively select a point, select all, inverse selection, to group and group, to snap, and to export super mesh elements. So let's build a domain from this. So we can use the new add 3D super mesh bonding surface tool. We can say that the base of the system is 0 meters. So we have now the domain. So you have the domain, and with this domain, so we can start adding a number of different information. So let's try to digitalize some simple geological horizon. So that was not a good idea. I have it here. If I plot the points, so these are points, which you will see it in a minute. If I change some settings, I need to tell FEFLOW that I would like to plot them in 3D. And they have an attribute, the points, which is called horizons. I have just 3 horizons, A, B, C. We can also change some colors. So that's too not visible. Okay. And let's make the lines a bit thicker. Apply. So we have these points, and these points are defined in certain geological conditions. So we can use our tool, something very simple, to digitalize the surfaces. So we can also tell FEFLOW I would like to snap using points coming from the map. And let me see what is the first one. Yeah, the one in red. And if FEFLOW automatically will identify the location of the points, and then you start building different surfaces. So this is quite simple exercise because we are running out of time, but obviously you can digitalize a number of more complex informations if you want. So I can add 2, 3, as many as I want. If of course, if I have a lot of surfaces, probably it's better to do it outside FEFLOW. This is the possibility. It's a possibility as well. So you can import different surfaces with a typical super mesh workflow. Yep, here. So I can use that. And if we call some super mesh processing tool, so we can get rid of the rest of the surfaces, it's gonna take probably also a few seconds. So I can use the time in parallel to see the questions. Okay, or probably I leave the questions at the end because it's finished. So we can build the surfaces. If you run the mesh generator, so you will have, there is a problem because I need to clean the surfaces. Sorry, I need to remesh the surfaces first, which will looks like this. So the surfaces now are a bit cleaner, and this is meshable. So that's the mesh, and you have the different blocks and the different surfaces. Okay, you, for example, would like to edit something. You would like to do a test by removing one of the horizons. So now, nicely in FEFLOW, you can see what you are selecting. So you can choose the plane, select, and then do some operations. So I would like to delete this part, delete, and I deleted. I would like to remesh again and see what's happening. So if I build a model again and now activate as polygon, so I should see now only the 2 planes. So that's the whole idea of the new tools available in the 3D Super Mesh. They will allow you to build better 3D Super Meshes to edit part of information. So we also have the typical case where you want to have a river on top of your model, and if you are doing unstructured meshes that can be quite tricky. So we have a new method where you can project something on the surface, or we can call the surface edge path, and will identify the surfaces that you have, and then it will project the river on top. So if you create a mesh of that, you will have a selection of the edges where you can apply your boundary condition. The surprise, so we will have the next year, the FEFLOW International Conference is in October. Unfortunately, we're still really pending on the final confirmation of the venue, but it's very probable it's gonna take place the first weeks of October in Hamburg. But for now, save the day, October 2024, Germany FEFLOW International Conference. We will make an announcement soon in the next email communications where you will know more about this. And how do you get the software? We have the direct link. You can go to My Power by DHI, downloads, and then you will find My 2024 and find FEFLOW A1 for the downloads. This will be an in-person conference, so we would really like to have the personal connection with the participants, and we will have a number of workshops and also user presentations. I would like to thank you for participating in this webinar release webinar. We have one webinar, the last webinar for the year in December. This will be a special webinar which is intended to just answer questions. So if you have any question about FEFLOW, if you have been participating in the webinars before and something was not clear, or if you have any topics, send questions to my email address. I'm collecting all these different questions from different FEFLOW users around the world, and I will spend 1 hour discussion to cover all these answers in the next FEFLOW webinar in December. Thank you for participating. I hope you install and try A1, and looking forward to get your feedback about this new release. Thank you, and until the next time, bye.